a recent study of adsorption, diffusion, and reaction in pillar clays. The paper is co-authored by M. Salini, M.L. O'Sully, and P.T. Tsotis. The speaker is M. Salini. He and Professor Tsotis are associated with the University of Southern California, and Dr. O'Sully with Unocal Corporation.
First of all, I should acknowledge my graduate student, Valerie Zhu, who has done most of the work because on the oversight their name was deleted from the small book, but as you may notice, her name is included in the book of the extended abstract. I don't have much time, but let me summarize what our goals are. Our goals are to develop a predictive model of diffusion, absorption, and reaction mounted in a restricted environment in general. That's my research program with Valerie Zhu at USC. And then more specifically, we want to estimate the diffusible organic molecules in pillar clays under reactive and non-reactive conditions, so that we can explain the experimental observations and data. And then hopefully later on, when we understand these things, we explore the possibility that there might be a scaling up between diffusivity and molecular weight of the molecules in such environments, so that we can estimate the diffusivity of similar molecules without actually doing any experiment or any simulations. So let me just quickly go over and remind you, pillar clays are a new class of catalytic materials that are used for converting gas oil into transportation fluids, and their cracking activity is compared to zeolite-based commercial food cracking catalysts, but they don't have the hydrothermal stability of zeolite-based of catalysts, and that's one reason they haven't been used extensively. And the way they are made is by exchanging aluminum hydroxide cation in Na or Ca benthonides. If you want to see how they look like, they basically look like this. And here we have oxygen with this, and hydroxide, and aluminum, and so on. So they look, and as you notice, they look very regular. As far as imagining exactly how they look like, this is the way they look like. There are taller sheets here, and very restricted space between sheets. These dots are pillars that connect any two sheets. There are holes through which the molecule can escape from one layer to the other. But if the molecule is large enough, they can't pass through these holes, and therefore, in the simulation that I'm going to talk about, we only work with two parallel sheets and the pillars between them. So that's. Now, although they look very structured and very simple, there are some subtleties of transport phenomena in pillar clays. First of all, as you notice, they have very restricted structure. They are almost two-dimensional. Second, they may have a fractal structure. What it means is that if you take the volume of the pillar clays and then you try to correlate it with some sort of length scale in the system, then you have a relation that V goes like L to power dF, where dF is called fractal dimension. Now, what is the significance of this is that if pillar clays were exactly 2 or 3-dimensional system, that dF would be 2 or 3. But some experiment by Pripyat and co-workers, and also by Mario Ocelli at UNITA, may indicate that dF is not actually 2 for a 2-dimensional system. It's less than 2, it's 1.9. So if it is true that it has a fractal structure, that means that transport in such a system cannot be described by classical continuum equation diffusion reaction. We already know that if you have a fractal system and you have diffusing molecules in that fractal system, we can't use continuum, the classical continuum diffusion equation with constant diffusivity. So if this is the case for pillar clays, we may be in trouble in that sense. Now, if we do have a fractal structure, that means that if you have a diffusing molecule in such a system and you calculate its mean square displacement, from the Einstein equation, this minuscule displacement should go like 2 times the effective diffusivity times the dimension of the system times time. Or you can use it as a definition of DE. DE is the ratio of the minuscule displacement and 2 dt, where DE, as I said, is effective diffusivity. Now for fractal system, this minuscule displacement varies with time, or for all systems. Now, for fractal systems, this minuscule displacement varies with time like t to some power delta. If we had a Fickian or Gaussian diffusion, normal diffusion, then this delta would be 1. But for fractal system, this delta is less than 1. Which means that the effective diffusivity, which is the ratio of this minuscule displacement and 2 dt, scales with time like t delta minus 1, which means it varies with time. And since delta is less than 1, that means that diffusivity ultimately vanishes. Now, the closer delta to 1 is, the slower the variation of dE with t. But if you do experiment or if you do simulation and you find that dE varies with time, even slowly, that may be a signature of a fractal structure. And in fact, I argue from simulation that that may be the case. Now, how do we do computer simulation of diffusion and transfer phenomena in pillar plates? We do it the following way. If you are interested in looking at diffusion in pillar plates, what we do is we represent the diffusion process with a random walk. And then we calculate minuscule displacement of the diffusing molecule as a function of time. We calculate their effective diffusivity from the definition I told you. And this is basically what we call a dynamic Monte Carlo approach. The precise steps of the Monte Carlo approach are as follows. First of all, we generate the structure of the pillar plates on a computer. Those pillar plates that I'm familiar with have basically very regular structure, and we know the location of pillars and everything. So we can basically exactly generate their structure on the computer. So that involves no approximation. We know the dimension of the pillars, we know the distance between the two parallel sheets, and so on. So we can do that on a computer. And then we also vary the distance between the pillars or between the sheets in order to look at the effect of that on transfer process. Then what we do is, in order to follow the motion of molecules, we assume that the space between two sheets have a structure like a cubic network. In other words, the steps that the molecule takes between the two sheets between the pillars and follows the principal direction of a cubic network. But you can assume it. You can assume any other structure. You can assume that the molecules do a Levy-Fly, which means that they take a random direction at every time step with a random angle. You can also do that. That would make it more complicated as far as computer simulation is concerned, but there's no major problem as far as doing it. You just have to work harder, which you are perfectly willing to do it anyway. Then what you do is, then you do the diffusion of molecules in the pillar plate after generating the pillar plates on a computer. What we do is, you can do it two ways. You can inject one molecule in the system, follow its motion, calculate all the quantities you want, and then you inject another molecule. You do the same thing. You average it over all quantities and all time and so on. This is the case of tracer diffusion, or the case that a molecule does not see another molecule, so that you can follow one molecule at a time. That's one way of doing it. The other way is that it is more concentrated, so that you have to inject many molecules into the system. You have to follow their motion. In principle, you have to take into account the interaction of the molecules with each other, with pillars and with the parallel sheets. But for most of the experimental data that I have seen, the system operates at low temperature and very low pressure, which means that most of the interaction between the molecules can be neglected, except of course the hardcore repulsion, which means the excluded volume. No two molecules can occupy the same space at the same time. So we do take that into account now. Valerie and I we are getting ready to do full molecular dynamic calculation, which means that we take into account all forces. But that would be for the future. Then what we do is we let the molecules do a random walk around the axis of the cubic network, and if the molecule hits one of these parallel sheets, we just reflect it back, because experimental data indicates that there is no absorption on these parallel sheets. If the molecule crosses the boundary of the system, we just remove it from the system. So that's just like experimental situation. Now, however, if the molecule hits the pillar, then we let it absorb on the pillar with a probability p, which is basically a Boltzmann factor of exponential minus c epsilon I, where c is a constant, epsilon I is the binding energy between the molecule and the pillar. If the molecule is absorbed on the pillar, we let it just sit there forever because there might be little desorption. But however, if there is desorption, we can assign another probability from the physics of the problem for desorption and let the molecule be released into the porous space again and then continue its motion again. So once you did that, you are basically home. So what you do is, when all the molecules have made one attempt, then you increase the time, and then at any time t, you calculate the mean square displacement, and you also calculate the volume fraction of the porous space that has been occupied by the adsorbed molecule, and you follow that. You calculate mean square displacement from which you calculate effective diffusivity. So you can do that, which is what I originally mentioned. The effective diffusivity is mean square displacement divided by 4t or something along that line, and you continue the simulation until the volume fraction of the space occupied by the molecules, which is a constant value. In other words, you have absorbed so many molecules on the pillar that you can't send any more molecules into the system, and they can't diffuse because most of the porous space has been blocked by the absorbed molecules. And then what you do is you repeat the entire procedure because you originally put the molecules randomly into the system. You repeat it, you calculate the same quantities, and then you average it again. And then you do it as often as you can until your averages do not change with more simulation. Now let me show you some results and then make some observation of experimental data. Here I have the effective diffusivity versus the width of the pillar, and I have it for most of various size. In this simulation that I'm showing you, they have put needles. They only have one dimension. So I have a needle of length 3 and a needle of length 3 again, but with different, here I have absorption probability of 0.01, and here I have absorption probability of 0.1, and then for a needle of size 5. And as you can see, originally they're different, but as you increase the width of the pillar, you basically approach the same thing, because if the pillar can get too close to each other, these molecules cannot diffuse through the space between the pillars. So it doesn't matter whether you have a needle of length 3 or needle of length 5. The diffusivity is very low, and they are basically similar, which is expected. Here I have the variation of the effective diffusivity with the width of the pillars again, with no adsorption. This is a molecule size 1 in terms of the lattice space, size 3, size 5, and size 7. As you can see, it decreases with the size of the molecule, which is again expected. But the simulation actually shows it. Now let me, since I don't have time, let me show you something that is relevant to experimental data directly. Here I have the diffusivity of the molecule versus time. We calculate the diffusivity molecule, and then we follow it until it basically becomes a function of time. Rho 0 is the volume fraction of the porous space originally filled with molecules, so 10% and 20%. As you can see, the D appears to be a constant after a while. However, if you look at it very carefully, you'll see that it's still changing with time very, very slowly. And if you remember what my discussion was fractal, if delta, that exponent of mean square displacement related to time, is close to 1, then D value is with time very, very slowly. So given that we basically have the structure of the pillar almost exactly similar to the computer, that may indicate that yes, pillar clays may indeed have a fractal structure. And that means that D varies with time very slowly. And in fact, the experiment that Mario Uccelli has done at UNICAP confirms it. They observed that D varies with time. Now, it may be because they didn't wait long enough, or it may be because we didn't wait long enough, but at least this is some indication that the system may have a fractal structure, both in academic simulation, theory, and experiment. The same thing here. Here is diffusivity versus time for various sizes and so on. You'll see that. So if you want to make exact observation, from our simulation, we make the following observation. If the molecules are relatively large, their effective diffusivity appears to vary with time, which is what I just told you, even after relatively long time. And even for a small molecule, we find that they still vary with time, but much more slowly. There is another aspect of experimental data that I should mention, and then I'll finish my talk, and that is, when enough molecules have been absorbed, we can no longer have molecules that diffuse effectively in the catalyst. but there is a still open space in the system, which means that the system basically has been saturated. The adsorbed molecules block the rest of the molecules from diffusing. And so we can calculate the volume fraction of the pore space at the end of the simulation, which is still empty, but the system has been saturated. And if we do that, we find that we get a behavior like that. This is the volume percent of the volume fraction of the pore space occupied by the molecules, and this is versus time. As you increase time, you run the simulation, you eventually reach a point where it doesn't change with time anymore. For this system, this is about 65%, which is in agreement. For this system, we put molecules that look like cubic structure with 3 effective dimensions, which we feed it to certain hydrocarbon, and the number that we got, 65%, is in fact almost in precise agreement with like 5% difference. This is the experimental point with experiment. So it basically does give you some indication that the simulation is working. So if I want to draw any conclusion, we have developed a dynamic Monte Carlo for diffusion and absorption of molecules in pillar clays, which seems to be capable of producing results that are consistent experiment. The size of the molecules and the restricted structure of the pillar clays have very strong effect on transfer processes inside the system, and therefore we have to be careful about how we describe transfer processes inside the system. This is where I stop, and I thank you for your attention.
Thank you very much, Professor Fahimi. We don't have right now any time for questions, so if anybody has a question to Professor Salini, please ask it after the session or after this paper. Next.